Existence and uniqueness of solutions for initial value problems. Let us consider three initial value problems. The absolute value of the derivative of y plus the absolute value of y equals to 0 with the initial condition y of 0 equals to 1. Equation number 1. Second, derivative of y equals to x with the initial conditions y of 0 equals to 1. And the third initial value problem, x times derivative of y equals y with the initial condition y of 0 equals to 0. Here, the first initial value problem has no solution. This is because y equals to 0 is the only solution, that is, y of x is equals to 0 for all values of x. The second initial value problem has precisely one solution given by 2y equals x squared plus 2, and the third initial value problem has infinitely many solutions given by y equals to c times x, where c is an arbitrary constant with y of 0 equals to 0 for any values of c. From these three examples, we say that an initial value problem given by y prime equals to f of xy with the initial conditions y of x0 equals to y0 may have no solution, exactly one solution, or more than one solution. This fact makes us wonder about the existence and uniqueness of a solution. Problem of existence. What are the conditions under which an initial value problem of the form have at least one solution? Problem of uniqueness. Under what criterion does the problem have only one solution, thus denying the possibility of more than one answer? Existence theorem and uniqueness theorem are the name given to theorems that state such criteria. While such theorems are not necessary while working with simple ordinary differential equations as stated in example 1, 2 and 3, nevertheless, for complicated ordinary differential equations, such theorems may be quite useful and in fact necessary. Even if we are certain that our physical or other systems operate uniquely, our model may be oversimplified and may not accurately represent reality. Theorem number 1. Existence theorem. For the first order initial value problem given by y prime equals to f of x, y with the initial condition y of x0 equals to y0, equation number 1. Suppose f of xy is continuous at all points x, y in some rectangular region R in the xy plane, that is, R is equals to the point x and y with x lying between a and b and y lying between c and d. And f of x, y is bounded in R, that is, there exists a number k such that the absolute value of the function is always less than k for all values of the point x, y belonging in the region R. Equation number 2. Then the initial value problem has at least one solution phi of x in some interval, absolute value of x minus x naught less than delta, where delta is some positive number. According to theorem 1, in the region R containing the point x naught y naught, if the function fxy value of the given initial value problem is continuous in that region about the point x naught y naught, then the initial value problem has at least one solution. Theorem number 2. Uniqueness theorem. Suppose the function f of the initial value problem and its partial derivative with respect to y is continuous for all x, y in the rectangular region R and bounded as well. That is, the absolute value of the function is less than k and the absolute value of the partial of f with respect to y is less than m, where k and m are some positive number, then the IVP has at most one solution, y of x. Thus, by theorem number 1, the problem has precisely one solution. Theorem 2 warrants that the initial value problem has at most one solution if partial of f with respect to y exists and is continuous within the region R. Let's understand the theorem with the help of few examples. Example number 1. Consider the initial value problem. Derivative of y equals y squared with the initial conditions y of 0 equals to 1. Clearly, the function f of xy equals to y squared and partial of f with respect to y equals to 2y are both continuous in any rectangle containing the point 0, 1. So the hypotheses of theorem 1 and 2 are satisfied. Consequently, it follows that the initial value problem has a unique solution in an interval about x equals to 0 of the form 0 minus delta, 0 plus delta, where delta is some positive number. Y equals to 1 over 1 minus x is the unique solution to the initial value problem. Problem number 2. Let us consider the initial value problem y prime equals to cube root of y. With the initial condition y of 0 equals to 0 and t greater than or equals to 0. Here the function f, which is given by y raised to the power of 1 over 3, is a continuous function in any rectangle containing the point 0, 0. The theorem 1 suggests that the given initial value problem has at least one solution. So using some standard method, we will get y equals to 2/3 of t plus c whole raised to the power of 3 over 2. So this is the solution. If c is equals to 0, the initial condition is satisfied, and that was going to give us y equals to 2/3 of t whole raised to the power of 3 over 2, and this is going to be a solution for t greater than or equals to 0. However, partial of f with respect to x gives us 1 over third y raised to the power of 2/3, which is not continuous or even defined at y is equals to 0. Consequently, there is no rectangle containing the point 0, 0 in which both f and partial of f with respect to y are continuous. We cannot say for sure that there is at most one solution. There could be more. In fact, y equals to negative of 2/3 of t whole raised to the power of 3 over 2 and the identity y 0 are also two solutions for t greater than or equals to 0.